All right, welcome to Thermodynamics, and this is Chapter 5, Part 1. I am Ms. Bedrosian, and we are going to break this up into two sections. So let's look at the definition for work, just in the book. This is the energy required to move something around, used to cause an object with mass to move. And the partner that goes with this is heat. The definition for heat, this is also energy. This is the energy used to cause the temperature of an object to rise. So these two things are part of every reaction. The units that we usually use for energy are as follows. 1 joule is 1 capital J. This is also equal to 1 kilogram times meter squared over second squared. We use this one as well, not as frequently, in some equations later. And of course the calorie, 4.184 joules. But the one that we use the most is the joule or kilojoule. This is the one that is most commonly used in our problems. All right, we usually have to divide it up as system and surroundings. In chemistry, the system is the reaction that's occurring. So we always look at the reactions in terms of the system. That's the system. Everything else is the surroundings. If we take a look here, if energy is going into the system, that means it's endothermic. And the surroundings are getting colder. If energy is coming out of the system, it's exothermic. Oh, let's draw a little picture. This is a little sheep. And the sheep will be saying, let's review the first law of thermodynamics. You probably know this. And this is energy is conserved. You know, what goes in must come out. The energy going in must equal the energy going out for a system. E is the sum of all the types of energy in a system. The truth is, we can't actually know E, because there's energy embedded within the atom, within the nucleus, within the electrons, between the nucleus. So this actually can't be determined, the exact E of a system. So what we can measure is delta E, change in energy. That's equal to Q plus W. Q is heat and W is work. I will keep repeating this. Know your signs. It is really, really important to know your signs. So adding heat, that's Q, to the system causes Q to be positive. If work is done on the system, then W, or work, is positive. Know your signs. This would actually cause delta E, change in energy, to be positive. So the question for you is, what does it mean when they're all negative? What does it mean if Q, W, or delta E are negative? And I ain't gonna tell you. You need to figure it out. So go do it. Look it up. All right, here is the great state of Ohio, because we're going to look at what's called a state function. So a state function is when the value depends on the present state, not how it took to get there, not on the path the system takes to actually get to that state. It's the state in real time. Like right now, what's that state? So for example, if you wanted to go party down at OSU, you could take a car. You can go from Cleveland to Columbus. If you were very wealthy, maybe you could take a private jet. And you could go by private jet from Cleveland to Columbus. Different ways of getting there. But no matter which way you choose to travel to Columbus, Columbus is 1,100 feet above sea level. That will not change no matter how you get there. That's a state function. And delta E is also a state function. So the change in energy for a system is considered a state function. Now, we usually use the term enthalpy more than E because the reactions take place in the real world. This includes the factor that all reactions take place in the atmosphere, where there is pressure and volume of the air having an effect. So delta H enthalpy is equal to delta E plus pressure multiplied by delta volume. This is the equation that's most likely that we're going to see. When delta H is positive, then the system has gained energy. So is it endo or exo? It is endothermic. It's gaining energy. And on the flip side, if delta H is negative, then the system has lost energy. So energy is coming out of the system, so it is exothermic. Again, let me repeat, know your signs. You really have to know your signs. This will come up again and again. We're going to stop here. This is end of part 1. All right, welcome to Thermodynamics.